So in Cortex, you have the ability to output joint kinematics and subsequent kinetics. However, a model is needed in order to get these calculations displayed and exported into Excel. So a model includes not just the markers, these are the real markers that are placed on the body, the virtual markers, which typically are used to define joint center locations, and then the segments themselves. Now, the segments are what's known as skeletal segments. These are three-dimensional coordinate systems that are defined for each segment of the body. So we call them segmental coordinate system. There are three types of quote-unquote skeletons, skeleton engines. There is calcium, there's a hybrid, and then there's SkeleonBuilder, which is relatively speaking a fairly simple engine to use to develop a model. In fact, for a novice user, it typically would take less than an hour to actually develop a full body marker, full body skeletal model. So in this case, we're just going to do a couple segments. So if you click here on the marker set properties, you'll see everything associated with that marker set, the real markers, virtual markers, the links, and actual segments. So first thing you need to do is make sure that you have SkeleonBuilder selected as your skeleton engine, and you would have to be licensed in order to use this SkeleonBuilder engine. Rotation order is the Euler sequence in which the kinematics are calculated. So in this case, we'll use ZYX. We'll define the bone axis as Y, and we'll go ahead and create a brand new segment here. I'll call this pelvis. And in pelvis, if you look down here, you can edit the properties for that specific segment. So pelvis, its parent segment will be global. Parent segment simply means the reference segment to which kinematics and kinetics for the specific bone segments are calculated. So we'll choose global. And each skeleton segment is defined by essentially three markers, and those markers can be either real markers or virtual markers. So basically 3 points. So for this segment, we'll use, and I already took the liberty in creating the necessary virtual markers for the segments that we're using for this tutorial. So we'll use mid pelvis, long axis. So 2 points define a vector, 3 points then define the plane or the three-dimensional coordinate system for that segment. So go mid-hip. Plane axis is the non-collinear marker. So any marker on the same segment. So we'll use a real marker here, and then we'll just use, I believe I have right ASIS or iliac crest, left iliac crest. So if I go ahead and calculate skeleton here on the left side, can't really see it, but you can see that Cortex defined a three-dimensional coordinate system for the pelvis. So obviously the assumption in all this is that each skeletal segment defined is one rigid segment. So that's the pelvis. We'll repeat those steps for, let's call this the right femur or thigh, whatever you want to call it. We'll call this the right femur. So for the right femur, its parent segment will be the pelvis. This means that all femoral rotations, this is hip flexion extension, abduction adduction, internal external rotation, will be calculated relative to the pelvis. So this is a relative angle. And its segment is defined from the right hip joint center to the knee joint center, or knee joint location. And we can use any marker on the thigh itself that is non-collinear from the first 2 points. So we'll use the right greater tongue canter. Go ahead, hit calculate. And now you can see that we have a 2-bone skeleton, pelvis, and then femur. And from here, we can calculate right hip joint flexion, extension, abduction, adduction, and internal external rotation. So this is simply femur rotations relative to the pelvis. And we can repeat the same thing for the tibia, the foot, and if you have an upper extremity model for the shoulder, elbow, and wrist. Now another useful tool in SkeletonBuilder that's pretty straightforward to use is the adjustment of the rotational offsets in all three axes. Depending on the type of model you're using, typically you would like the neutral or anatomical position to be zero. So in this case, you've got the right femur that will be measured relative to the pelvis, but as you can see here from the axes, actually let me turn off link so you can see the three-dimensional three-dimensional axes for the pelvis and femur, and you can see that they're rotated about 180 degrees. So I'm going to go ahead and adjust that. Just click here on the right femur. So we're going to do 180 degrees about the bone axis. This is the y-axis. Hit calculate. And you can see now that if I were to calculate kinematics, that neutral will actually be 0, close to 0. So you can do these offsets depending on how you have your segments defined in any of the three axes for that particular segment, so that you can actually make them neutral at 0.